Alright, hey folks, remember here for your exponential function, f of x equals b to the x. Remember, b is the base. Base, it's a number between 0 and 1, not equal to 1. Remember that what I've just sketched the graph is kind of to remind us of like the exponential growth. So this would be exponential growth. So the base here would be a number larger than 1. Couple of facts. Remember, this is a point on the graph, and remember that the domain is all real numbers. The range is 0 to infinity, so you can put anything in for x, and then the y's that come out are 0 to infinity. And then remember, we made an observation way back in an earlier video that it is a one-to-one function. So since it is a one-to-one function, that means it has to have an inverse function. So what I've graphed over here, I've sketched a graph of its inverse function. Now remember, its inverse function would have a domain that's equal to the range here, and a range that's equal to the domain. That's just our old property, our old knowledge of a function and its inverse function. So the domain of the inverse function is 0 to infinity, and the range is negative infinity to infinity. A few more things. The point 0, 1's on the graph of the function, so that means the point 1, 0 is on the graph of the inverse function. The only thing I haven't done yet is give the inverse function a name. It does have a name, and its name is log base b of x. Log base b of x. That's how I read that. Log is short for the word logarithm. So what we're going to be doing in this video is, I'm going to go over a couple of facts about logarithms, how we can look at some properties of logarithms, evaluate logarithms, and we'll eventually talk about domain of logarithms. But I wanted to start this video off with something old and something that we've already talked about and how it gives us something new. So when we come back, I'm going to give a quick definition of how to go from exponential form to logarithmic form and vice versa. So that'll be the next thing that we look at. Alright, next we're going to look at the relationship between logarithms and exponents. So logarithms and exponents. They're inverse functions, so they should be related somehow. Y equals log base b of x if and only if b to the y is equal to x. So that shows us how to go from a logarithmic form to an exponential form, or if we have something in exponential form, how to put it back into logarithmic form. Here, let's look at an example. I'm going to make a couple of columns here. Exponential form and its corresponding log form. You should be able to write them the same way. So let's look at this exponential form. 2 to the third power, we know that is equal to 8. We can write this equation in a completely equivalent form as logarithms. It would be log base 2 of 8 equals 3. Notice the base of your exponential form and the base of the logarithmic form are the same. So you can take an exponential beastie and put it into its logarithmic form. Let's try another one. 3 to the fourth is equal to 81. In logarithmic form, we would have log base 3 of 81 is equal to 4. I should be able to give you something in logarithmic form and you write it in its corresponding exponential form. So let's try one of those. Let's say you're given log base 2 of 32 is equal to 5. In exponential form, that would be written as 2 to the fifth power is equal to 32. So I wanted you to see it's a two-way street. You can take an exponential equation and write it as a logarithmic equation. If you have a logarithmic equation, you can write it as an exponential equation. Next up, I'm going to show you how to use your knowledge of exponential functions and their graphs in this inverse concept to get the graph of a logarithmic function. Alright, hey, before we do an example of graphing, I thought I'd write this up on the board one more time. The exponential function b to the x has an inverse function of log base b of x. So those two functions are inverses of each other. So hey, when I'm asked to graph f of x equals log base 2 of x, actually the first thing I graph, and I'll make a note right over here, that I'm going to graph the inverse function of log base 2 of x. Its inverse function is 2 to the x. I know what the graph of 2 to the x looks like. It's an exponential function. The base is greater than 1, so it's an exponential growth. I can find a couple of points. If x is 0, y is 1. If x is 1, y is 2. If x is 2, y is 4. I can get the graph very quickly. This is stuff I already know. This is the graph of 2 to the x. And now I can use my knowledge of the fact that the graph of an inverse function is symmetric about the line y equals x with its function. Remember, function and inverse function, the graphs are symmetric about the line y equals x, to get the graph of log base 2 of x. So if I sketch in the line, let me try this colored chalk. If I sketch in the line y equals x, I'll dash it. So there's the line y equals x. And then I just plot some points. You know, if 0, 1's on the graph of the function, then 1, 0 is on the graph of the inverse function. If 0, 1's on the graph of the function, then 1, 0 is on the graph of the inverse function. Pointed to the wrong point there. If 1, 2's on the graph of the function, then 2, 1 is on the graph of the inverse function. If 2, 4's on the graph of the function, then the point 4, 2 is on the graph of the inverse function. That should be enough for me to sketch the graph of log base 2 of x. It's got to look something like this. That is, I'll draw a little leader line, that is the graph of log base 2 of x. So when I'm asked to graph a logarithmic function, I end up really first graphing its exponential function. Then I use my knowledge of inverse functions to get the graph of whatever the logarithmic function is. I'm using something I already know. And that's it for this example on how to do the graph of a log function, log base whatever function. Next up, we're just going to do some, we're going to look at some properties, some basic properties of logarithms, and then we'll do some evaluations. Alright folks, next up some properties I need you to know about logarithms. The first one is log base b of b is equal to 1. So it doesn't matter what b is, as long as it's the same, log base b of b is equal to 1. Log base b of 1, well, that's equal to 0. And these both are just direct results of taking exponentials, logarithms, being able to rewrite them, rewriting logarithms as exponentials. Property number 3 says log base b of b to the x. That would immediately simplify down to x. And then property 4 says b to the log base b of x. It would simplify down to x. Now both 3 and 4 are a direct result of the fact that b to the x and log base b of x are inverse functions. Remember, when you do the composition of inverse functions, you have to get a result of x. That was our definition for knowing if functions were inverse functions. You did the composition, you got x. So that's what these are a result of. I'm just going to try to, excuse me, I'm going to just try to squeeze one of them in here real quick to show you that, that there's something to this. So let's say if f of x is b to the x and g of x is log base b of x. Let's do the composition. F composed with g of x, which is the f of g of x. They are inverse functions. We know this composition has to be x. Well, if we do the composition, f of, well, g of x is log base b. And then remember to evaluate function f at log base b of x. You're going to take that mess, log base b of x, you're going to toss it into function f wherever you see an x. You get b to the log base b of x. But because they're inverse functions, this has to equal just enough room to get the x on there. So if you were to now do the g composed with f of x, the gof of x, if you were to do that, you know because they're inverse functions, g of f of x has to simplify to x. That's how you would end up showing that property number 3 is true. But I need you to know these properties. So let's just practice using these properties. This example, I'll just give the simple directions of evaluate the following. And the first one, log base 4 of 4. Well, log base 4 of 4, looks like I'm going to use property 1. That immediately simplifies to 1. Hey, this is pretty easy stuff. Part B, log base 8 of 1. Well, that looks like we're using property 2. Log base b of 1 is 0, so log base 8 of 1, that's 0. Kind of looks like a donut. Part C. Let's simplify 3 to the log base 3 of 5. This is kind of looking like number 4 here. B to the log base b of x simplifies to x. So 3 to the log base 3 of 5, that just simplifies to 5. Hopefully these are pretty friendly and you're saying, hey, cool. Let's look at D. Log base 4 of 64. Well, notice log base 4 of 64. Notice 64. 64, I can rewrite 64 as 4 to the third power. 4 times 4 times 4 is 64. So I can rewrite this mess as log base 4 of 4 to the third power. Kind of looks like property 3 now. Log base b of b to the x simplifies to x. So log base 4 of 4 to the third power, that's right, it just simplifies down to 3. Let's do one more. I have just enough room here. Log base 3 of 1 over 81. Okay, I kind of see this as log base 3 of 1 over 3 to the 4th. 81 is 3 to the 4th power. And then, well, that is log base 3. Remember, 1 over 3 to the 4th, I can use properties of exponents and write that as 3 to the negative 4th. And sure enough, I'm just using property 3 again. This would simplify down to negative 4. So those are the first look at some special properties of logarithms. Know those properties of logarithms. It's going to make life a little easier. When we come back, we're going to compare and contrast two special logarithms, common log and natural log. All right, probably the two most popular forms of logarithms are what's called the common logarithm and the natural logarithm. The common logarithm is something like this. It's log base 10 of x. When the base is 10 and you have a common log, we don't write the base down at all. So you won't see log base 10 of x written. Instead, it will just be log. So when you just see this, log of x, it's understood that it's a common log and the base is 10. For natural logs, which is probably the most popular logarithm is the natural log. Natural log, the base is e. So it would look like this, log base e of x. You will not see it written like this. You will not see log base e of x written. Instead, you're going to see it written like this. ln x, natural log x. So when you see ln x, natural log x, you have to know the base is e. When you see log x, you have to know the base is 10. So that's your common log, natural log. Difference between the two. Okay. Hey, one final thing. We're going to look at finding the domain of a logarithmic function here in a minute. Way back in an earlier video when we were talking about first finding domains of functions, I said there were 3 bad things to worry about in function land. One was you can't have 0 in the denominator of a fraction. The second one was you couldn't end up with a negative number under an even indexed radical. And then there was a third one. And I didn't say anything about the third one at that time. I said you'll worry about number 3 later on. Well, now is later on. So the third bad thing in function land, or the third thing to be aware of, is that when we're talking about finding domains of functions, you can't take the log of a negative number. Or 0. You can't take the log of 0. So you can't take the log of a negative number, can't take the log of 0. So now you know the 3 bad things in function land, all 3 of them in their totality. You can't have 0 in the denominator, can't end up with a negative under an even indexed radical, and you can't take the log of a negative number. You can't take the log of 0 either. So let's see how this plays out in this example. Let's determine the domain of the function ln 2x plus 1. So I've incorporated the natural log here, so we're talking about the base is e. But keep in mind you can't take the log of a negative number. You also can't take the log of 0. So this 2x plus 1 is not allowed to be negative, and it's not allowed to be 0. So that means 2x plus 1, if it's not allowed to be negative and it's not allowed to be 0, that means 2x plus 1 must be positive. Well, write that down. 2x plus 1 has to be positive. Just solve this little inequality. You subtract 1 from both sides, divide both sides by 2. That's the domain. But let's write it. Let's write the domain in interval notation. So in interval notation, that's what you would have the domain to be. And that kind of concludes this example for this introductory look at logarithmic functions. So we're done with this example, done with this video. The next video, we're gonna do more special properties of logarithms. But thanks for watching.